let's continue our discussion of Bode plots, okay? So as you may recall, we went through and we learned all of the sort of lead up to how to plot them by hand. We had the, this discussion here where we sort of manually plotted some points and did them, but we want to learn how to sketch them straight from the transfer function easily. And that's why we did all this discussion. And the main takeaways were that, first off, you can rewrite the transfer function as a product of possibly a constant, first order terms, and second order terms. That's one of the big takeaways. The next one was that when you combine complex numbers, the magnitudes multiply and the phases add, okay? And we said that the adding part's easy, the phase adding part's easy. And if we take the logarithm of the magnitude part, the logarithms of the magnitudes add. So we said that we're sort of preparing to sketch these things by hand, and that's all of these facts are going to help us do that. Okay. So the next step is to do these sort of simple transfer function Bode plots and gain an understanding from these simple examples of how to construct larger order transfer functions. Okay, so let's do the easiest one first, the constant gain. So that is a transfer function. You could multiply the input by 5, and you could get an output, right? That's a transfer function. Doesn't depend on s at all, and so if you plug in s equals j omega, does it change what 5 is? No. So the magnitude of 5 is what? 5. And the phase of 5 is what? 0. What is the phase of negative 5? It's pi, right? What's the phase of negative 1? So I always am thinking in terms of the complex plane here. So imaginary, real, right? So negative 5 on the real axis is out here. So the phase is always measured from the positive real over to here. So it's pi, or 180 degrees. So, okay, so for a transfer function that is simply a constant real gain, the frequency response function is trivially just k, right? Just whatever the gain is. Its magnitude is magnitude k. For positive gain k, the phase is 0, and for negative, the phase is 180 degrees, or pi. Okay, so that's easy. We didn't even have to really draw it because the magnitude plot is going to look like a constant k, and the phase is going to look like either 0, constant 0, whoops, so constant k, and then the phase one's going to look like constant 0 or constant 180, so, or negative 180. They're equal to each other. Okay, so that was easy enough, constant gain one. So thinking about it in terms of combining it with other transfer functions, the gain just sort of shifts up the whole curve or shifts down the whole curve, depending on what the gain is. And the phase is going to either add nothing to it, or if it's negative, it'll add 180 degrees. So pretty straightforward. So the next simplest two options are poles and zeros at the origin. So example 1.1 is the example that we did last time, where we did a manual plotting of points straight from the frequency response function and found that found how to find how to derive the transfer function or the Bode plot from the transfer function h of s equals s, which is just a 0 at the origin. The frequency response function is plotted here. So this is the plot that we found in the example. Oh, no, wait. This is the one we found in the example. So this column here. So here's the magnitude in dB. It goes through frequency 1 and magnitude in dB 0. And it has a, let's see. It has a slope associated with it. So let's draw across here 0 dB and then 20 dB. Notice that it increased by 20 dB in this interval from 10 to the 0 to 10 to the 1, which is a factor of 10, right? So from 1 to 10. And it continues to increase at that rate. And this slope then is going to be 20 dB per, and then what we call a factor of 10 in omega is a decade, okay? Per decade. So you guys have heard of an octave, maybe, from music. That's a factor of 8, right? A decade is a factor of 10. So if you increase something by a factor of 10, you've increased it a decade. So the slope of this line is 20 dB per decade. And it goes through omega equals 1. Okay. And the phase for the, so this is the transfer function, just for the single 0 at the origin, is 90 degrees all the time, just always 90 degrees. And for a single pole at the origin, I said pole over here, didn't I? I meant 0. Did I say pole? I don't remember. Rewind the tape. This is a pole over here, 1 over s. That's a single pole at the origin, right? Because if s equals 0, the denominator goes to 0, and that means it's a pole. So this is the magnitude plot here. Notice that it looks sort of like the flip of this, or the reverse of this. It's actually the algebraic inverse of it. So if we looked at what happens in a decade, it once again travels 20 dB, but it goes down, right? So slope here is negative 20 dB per decade. But it's a straight line again, right? So once again, we have got these nice straight line plots, which are easy to plot by hand. You can plot straight lines pretty easily if you have a ruler or a steady hand or just computers to help you. And then the phase of this one just ends up being negative 90 degrees. So that's constant all along. So those are pretty easy, okay? And then we're going to consider 2 more classes, first order classes and second order classes, okay? First order real poles and real zeros, and then we're going to consider second order conjugate pole pairs, okay? So those are the ones we'll consider still. So the derivations for real poles and zeros are not included, but here are the results. So if I go through and I find the magnitude of the frequency response function, find the phase of the frequency response function, you can find a derivation in the textbook on this. It's just kind of, the first order is not bad. Second order gets pretty long. It turns out that the plots for these are very simple and predictable. And in fact, we we end up with a frequency response function that depends on omega, but wherever omega shows up, there's a tau multiplying it. So tau is the time constant from the transfer function. So if we've got 1 over tau s plus 1, that means that we have a real what? Yeah, well, so is it a pole or a zero? Pole. And this is going to be a real zero. So if you got the real pole, it turns out that wherever in the frequency response function, so remember we would find that by plugging in s equals j omega, right? J omega is equal to h of s evaluated at s equals j omega, right? So we plug that in, we chug through, and we could just plot it, right? Just from the definition of the dB magnitude of the frequency response function and then the phase, we just plot it. And this is what it turns out to be. Well, it turns out everywhere that omega shows up, tau shows up too, okay? And so we can plot on this horizontal axis. We're not plotting omega, we're plotting tau times omega, okay? The reason we're doing that, so there are a couple reasons. The first reason is that these plots then no longer depend on tau, right? So you can make these, this version, this plot, and this plot, this plot, and this plot. That's all the possibilities for a real polar zero, because it doesn't depend on tau, and so a real pole or a real zero always shows up like this. So this is exactly the plot every time. Now, if you wanted to know what this looked like without the tau in it, it's just going to be a stretching of the, a scaling of the horizontal axis, right? So you guys remember back in the day when you learned about scaling functions? You learn how to scale them in y, you learn how to scale them in x. So this tau omega is essentially a scaling of omega in the x direction, right? So that's what we've got here. And this is the other second reason to do it is that this is a dimensionless quantity, because tau is in units seconds and omega is in units radians per second. So the seconds cancel and you have a dimensionless radian quantity. And that's something that if you guys end up doing much research later on, if you're going to grad school, this is a common thing to do when you're doing plots, because it takes away dimensions from an axis, and oftentimes it makes the graph capture a lot more in one graph. So it's pretty cool, pretty useful stuff. So notice that, so let's look at the pole first, so the single real pole. So this is 0 dB, 0 dB, 0 dB, and then it starts to kind of break off, and it ends up at this other slope, but another straight line, right? So it's a straight line and a straight line, and then there's this little curve that happens. So this break point where the curve breaks, so I'll put a little vertical line there. This frequency, or dimensionless frequency, we might call omega tau, this occurs at omega tau equals what? What's 10 to the 0? 1. So this occurs at, if we solved for omega, this occurs at the frequency 1 over tau. Okay? And this, since this is a very important frequency for these real poles or zeros, we give it a name, and it's called the break frequency, okay? So, call it the break frequency.
Isn't it also called like a cutoff frequency?
It is if you're thinking of it in terms of a filter. So yeah, so if you're thinking of this as being a low-pass filter, then we would call it the cutoff frequency. Yeah. So this is the break frequencies are frequencies that are often cutoff frequencies for filters because the plots change there. Yeah.
Sorry, taking a step back here. So to make this graph, you're still just using that 20 log base 10 stuff to create this graph.
Right.
You're just plugging in whatever's in front of the J. So it would be.
No, so I'm taking the magnitude first, right? So for this plot, this is the magnitude.
Does that have like the whole thing, like out of that 1 over tau s plus 1? What are you taking out of that?
So let's come over here to the margin and let's see. So h of j omega is equal to 1 over tau times j omega, right? We plugged in for s, plus 1. And if we took the magnitude of the numerator and magnitude of the denominator, we can do that, right? And we could find the total magnitude. So let's just write immediately the magnitude of h of j omega is equal to, the magnitude of the numerator is 1. And the magnitude of the denominator is, this is a complex number, so you have to take the square root of, it's going to be tau omega squared, so this is the imaginary part, right? Tau omega squared plus 1 squared, just 1. So that's what the magnitude looks like. So this plot is exactly that, except for we plug it in to the dB, so h of j omega in dB is just equal to 20 log base 10 of h of j omega. And that's what this plot is.
Yeah, like the 10 negative 2, 10 negative 1, 10 0, that's what your omegas are that you're evaluating it.
Right. And notice how everywhere that omega shows up, it only shows up one place. Tau shows up with it. So we could either plot this for a bunch of different taus versus omega, or we could just plot it versus tau omega, which is what we do.
So is that the square root of TV squared or tau v squared?
It's tau omega. Sorry, that's not very clear.
Yeah, that's just you rationalizing that fraction, right?
So yeah, I could rationalize the fraction and then take the square root of the real part squared plus the imaginary part squared. What I chose to do is to find the magnitude of the denominator separately from the numerator and combine them that way. It's actually easier in this case. I often find it to be easier to do that. The definition that I said back in the notes was that you can rationalize first, and then you can find the real part squared plus the imaginary part squared. That's totally legit too. You can do it either way. You'll get the same answer.
So you're just taking the square root of everything squared. So
Yeah. Yeah. So the square root of the imaginary part squared plus the real part squared. Yeah. So that's this graph here, and then the phase is just going to be the arctangent of the imaginary over the real.
Of that same process.
Of the same process. Or I could find the phase of the numerator, phase of the denominator separately,
Right.
and then combine them by addition. Well, actually, it would be the numerator phase minus the denominator phase, right?
Just imagine you're real. So that the second line is your real, the 1 over omega, tau omega squared plus 1. That's your real.
So the one here, so the denominator has an imaginary part and a real part. So I'll just pull the denominator out for a second. The denominator has a real part, which is just 1,
Yeah.
and an imaginary part, so plus j times tau omega, right? So this is the real, and this is the imaginary. So if I want to find the magnitude of that, I have to find the square root of 1 squared plus tau omega squared. want to find the phase, I have to find the arctangent of the imaginary part, tau omega, over the real part, 1. And I can combine those phases by doing the quotient. So you can either convert this into a single complex number by rationalizing, and then apply the magnitude and phase, or you could find the magnitude and phase of the numerator and the denominator separately and combine them that way. So there's sort of 2 routes. Either one gets you to the same place. So.
Alright, cool, thank you.
Sure. Okay, so we're here and we saw straight line 0 dB until we hit the break frequency. And then what we actually have is a straight line from that break frequency down at. Do you guys want to look on the plot and tell me what the slope of that line is? Can you guys tell? Without me drawing. Target. I don't know why that is showing up. So for a whole decade, does it go down 1, or does it go down 10 dB, or does it go down 20 dB? Yeah, it goes down 20. It goes down 20 dB per decade. And the only other sort of feature here is that at the break frequency, it's at minus 3 dB, okay? So the way that we sketch these by hand is we draw the horizontal line at 0 dB all the way up to the break frequency, and then we draw a line that slopes down at 20 dB per decade. And then at the end, we round it off and we say, oh, it goes through negative 3 dB at the break frequency. So we do that little rounding part. So we draw the straight line, and then the rounding. So that's how you sketch a real pole magnitude. The phase is not bad either, but let's look at it for a minute. So the way to sketch the phase is, notice first off, it starts off at 0 degrees, and it goes to negative 90 degrees. Okay, and it has this transition, and it goes through negative 45 degrees at the break frequency. Okay, so at the break frequency, it should be a negative 45. And the method to draw this is to find negative 45 degrees and your break frequency, and that is a point on this plot every time. Then we take, we go back 1 decade, so 10 to the minus 1 decade, and we draw another dot on the 0 degree line, and then we go up 1 decade and draw a dot on the 90 degree line, and we draw a straight line in between them. And it's not a perfect approximation, but it's not terrible, right? It's a sort of straight line sketch of what that looks like. And then we say at frequencies below that break frequency minus a decade, it's 0. And at frequencies above the break frequency plus a decade, it's negative 90 degrees. So that's how we draw the phase sketch. Did that make sense? No? That was a little tough? Okay. So step 1, find the break frequency and put a dot at negative 45 degrees.
So omega equals 1.
Where omega equals 1 over tau, where tau omega equals 1.
Okay.
So remember we found that the break frequency shows up at 1 over tau. So we find that and we put a dot at negative 45 degrees. Step 2, go back a decade and draw a dot at 0 degrees. Okay. Step 3, go up a decade and draw a dot at negative 90 degrees. Okay. And draw a straight line that goes through those 3 points. And that is your approximation of what happens between a decade below the break frequency and a decade above, which, it's not perfectly straight, obviously, the real one, but this line, our approximation, is not terrible. So it gives an approximation for it.
And so what does this physically mean?
This means physically, so if our transfer function was giving us, so like in the example that we have for the vibration problem we're going to get back to, probably Friday, we have a transfer function that relates the input force to the force on the motor, on the base, right? That's what it was. So it was the input force to the motor, force on the base, I guess. Force on the base. So we have these two forces that we're relating to the transfer function. And we're saying that for a sinusoidal input at a given frequency, the steady state response, as we know, is just going to be a scaling of the sinusoid input and a phase shift, right? And that amount of scaling is at a given frequency, so at omega equals the break frequency, for instance. The magnitude is negative 3 dB, and so it actually decreases the output magnitude, the output amplitude of the sine wave is a little bit less. So negative 3 dB is a little bit less than the original. And the phase shift is negative 45 degrees. If you drove it at a low frequency, then the input amplitude would be exactly equal to the output amplitude. 0 dB, if you go back through the definition and you compute what it is in amplitude, it's just 1. So 0 dB is 1. So the output amplitude will be 1 times the input amplitude. So it'll stay the same. And the phase will be 0, so it'll be going at the same time. So that the amplitudes will be the same and the phase will be the same if it's going really slowly. But if you increase, this is the input, if you increase the frequency of the input, frequency of the output will also increase, but notice that the output amplitude is going to drop, right? This is the scaling factor of the input amplitude, so it's going to get smaller and smaller. And so what we're getting, if I can't do phase and amplitude at the same time very easily, but I'll try to do amplitude and amplitude. So the amplitudes are the same at low frequency, but if you're going faster and faster, the output amplitude is going to be smaller than the input amplitude, okay? It's also going to start lagging behind. So 0 degrees in phase shift means that they're coming along at the same spot. But 90 degrees means that they're opposite of each other, okay? So as you increase the frequency, let's see if I can do this. It's really hard, but it starts to lag behind. Ooh, I think I almost did it. I bet that looks really weird, doesn't it? But the idea is that it starts to lag behind the input by 90 degrees as you get to higher and higher frequencies. So that's physically what it means. Does that make sense?
It's a little more clear.
A little more clear? Okay. Yeah, it's. I mean, we're a little bit caught up in the weeds of the math right now, aren't we? And we're trying to learn how to sketch these things. We know what they are as far as they're ways of representing the relative amplitude and the relative phase of the input and an output. If you have an input that's a sinusoid. And then we learned how to represent it in this very sort of like idiosyncratic way, right? but this is the way that people represent it, so we need to learn how to do it. And it does have its advantages. That it's conceptually the same as, it's just a graph of the magnitude and a graph of the phase. So that's conceptually what it is, but all the details just are annoying, but we have to learn them. So, but you're right. I'm glad you pulled this out and got the high-level view. Like, what does this mean? Like, what does this mean? Okay, so thank you. So now we've sort of learned how to sketch these and what they look like. Let's learn how to sketch a real zero. Actually, it's exactly the opposite thing happens. It's very similar, very analogous. So at the break frequency, which is the same exact break frequency, 1 over ta, so we'll draw it in again. So once again, so I should put like a subscript b here for break frequency. Omega b is equal to 1 over ta again. It's this ta, though, the ta from the transfer function below it. And once again, the magnitude starts off at 0 dB at low frequencies, all the way up to the break frequency. It starts to kind of break off there, but close to it. And then it goes at 20 dB per decade, but positive 20 dB per decade. Oops. So this is a slope of positive 20 dB per decade. And instead of being at negative 3 dB at the break frequency, it's at, what would you guys call that? Positive 3 dB per decade. Or positive 3 dB, I should say. So at the break frequency, it'll be at positive 3 dB. So when you sketch this, you draw the straight line at 0, you draw the straight line at 20 dB per decade, and you go back to the break frequency and do a nice little rounding off at plus 3 dB, hitting it at about plus 3 dB. So that's how you sketch the real zero. So it's very similar. And same with the phase. The phase goes from 0 degrees to 90 degrees. So instead of going from 0 to negative 90, we go from 0 to positive 90. And once again, our method is to find the break frequency and put a dot on 45 degrees. We know that's on the graph. And it is precisely on the graph. It does actually go through that point. And we'll go down a decade, and we'll put a dot at 0 degrees. We'll go up a decade, and we'll put a dot at 90 degrees. And then we'll draw a straight line in between them. And that'll be our straight line approximation for that region. And the other regions, the regions below 1 decade below the break frequency, it's all going to be 0 in our approximation. And all of the frequencies above the break frequency plus a decade are going to be 90 degrees, positive 90 degrees in our approximation. So it's very analogous to what we had in the other case, right? Just flipped. Okay. Are you getting to see some symmetry here? Back when we did it's just on this page. So up here, you had a real, or so you had a pole at the origin, and you had a slope of negative 20 dB per decade, and a phase of negative 90 degrees. Here, once you get past the break frequency, you have a slope of negative 20 dB per decade, and a high frequency phase of negative 90 degrees. So the pole at the origin and the real pole are very analogous. It's just that one has a break frequency where this starts to happen, and the other one is always doing that. So you can think of the pole, or you can think of the pole at the origin as being a real pole for which you've already got to this high frequency asymptotic behavior of negative 20 dB per decade and negative 90 degree phase. So that's one way to think of it. Similarly with the 0 at the origin, we have a slope of positive 20 dB per decade and a positive 90 degree phase. At high frequencies, we have a slope of 20 dB per decade and a phase of 90 degrees for a real 0, right? So that's not at the origin. So this is a very similar sort of behavior. It's very analogous. And we're sort of learning, okay, if you put a pole here, notice you get this downward slope in the magnitude happening. Whenever you have a pole contribution, it brings high frequency magnitude down, right? Whenever you have a 0, it brings high frequency magnitudes up. So that's sort of the one thing. And then you have this shift of 90 degrees that happens, either negative or positive. So either starts to lag or it starts to lead. So we've got those sort of insights that we're gaining as we go through this. And we just have 2 more to do. They are the complex conjugate pole pairs, okay? So once again, we could go through and we could compute the frequency response function, h of j omega is just equal to h of s evaluated at s equals j omega, right? So we could do that again, and the transfer function for which we're doing that is h of s equals, so in the case of a complex conjugate pole pair, where you're doing it for the transfer function omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. And this is just, it's right here. I just wanted to write it just to be clear. But it's below the figure 1.3a right here. So if you expand all of this, what you'll get is h of j omega equaling some function that includes, so there's going to be, it's going to have a real part, right? It's always going to have a real part. If you want to simplify it down, you'll have a real part, and it'll have plus j imaginary, right? And in there, there's going to be these functions of omega that will show up, real part and imaginary part. You could take the magnitude of it, right? H of j omega. And you could take the real part squared and plus the imaginary part squared, take the square root. Do the same process we've done several times. And you would find these different plots for different zetas. Now, the horizontal axes are scaled here once again. They are normalized to omega divided by omega n. So it turns out that wherever omega shows up in this expression, it's divided by omega n. Well, I should say, if you rearrange it to have that, it shows up that way. So we can plot our new variable omega over omega n, which is, once again, it's dimensionless, which is convenient, and it allows us to plot fewer plots. However, we still have this zeta that's floating around, so we can't get rid of that by making it dimensionless somehow. So we have to plot different values of zeta. And I will talk about the magnitude of the poles, conjugate pole pair first. So if you've got a low frequency, notice that the output and the input have the same, so it's at 0 dB. So the output and input magnitudes are the same. And at low frequency, also the phases are the same. So it's just like the first order system, first order real zero or real pole situation, where at low frequencies, the magnitudes of the output and the input are the same, and the phases are the same. But as you start to get to higher frequencies, you go up to really high frequency, notice that the magnitude is dropping off at, so we'll look at, what is the slope that it drops off at? So this is 1 decade. So it's actually negative 40 dB per decade. Okay? So at low frequencies, it's at 0. At high frequencies, it's at negative 40 dB per decade. Another straight line. So 2 straight lines. So these asymptotes that we were talking about, they occur in the second order ones as well. Then what happens in here, we characterize by saying this is what's happening around the break frequency. So we call this the break frequency for one of these second order systems. So omega D, or sorry, B, omega B for break, is equal to, in this case, it's when omega over omega n is equal to 1, right? So it's when omega break frequency is equal to omega n, the natural frequency. Okay. So if we're going to sketch this, we could say that it's approximately a straight line at all frequencies below the break frequency. And it's approximately a straight line for all frequencies above, but at negative 40 dB per decade. And then you have to interpret the zeta, the damping ratio. So for high damping ratios like 0.9, 0.7, that straight line approximation is not bad. You could do some rounding if you wanted to. When you get to low damping ratios like 0.1 or like 0.01, you start to get this peak that happens. So let's go back to Jordan's question. What does this mean physically? This means that at this break frequency, which is the natural frequency of the system, if you have low damping, if you drive it with a sine wave at that natural frequency, the output amplitude is going to be larger than the input amplitude. This is a positive decibel ratio here, so we end up with more amplitude in the output. So if you have a motor mount that has like this resonance right there, that means that the force that's going in might be small, but on resonance, you could be applying a huge force to the structure. Okay? And that's why people have, there's this whole class on vibrations, and that's a really big issue.
So that'd be like an underdamped system? Or?
That's an underdamped system that can be driven to a high output amplitude from a small input amplitude. So all of this crazy phenomena that you see happening with bridges falling down or whatever, like that often comes down to a resonance that's happening that was unaccounted for. So rounding this off is just dependent on what the zeta value is, and you have to kind of have an idea of like a low zeta gives you more of a peak here and whatnot. So then what's left is the phase, and the phase, what we typically do for these is we say, okay, it's at 0 degrees up to the break frequency, and then it drops to negative 180, and the amount of rounding that we give to it just depends on the zeta value. I mean, it's not great. It's not a great approximation, but it's something. And as far as the complex conjugate 0 pair, which does happen, it's not super common, but it does happen. Well, it isn't super common in the problems that you'll see, at least. You will have just essentially the reverse of this. Instead of going at negative 40 dB per decade after the break frequency, it'll go at positive 40 dB per decade. And instead of going from 0 degrees up to or down to negative 180, it goes from 0 degrees up to positive 180. So those are the ways to do sort of straight line approximations. And notice that there's this notch that happens. So if you have these zeros, we call these things transmission zeros and vibrations. You can have this happen too, where you're driving with a force on something, say, and there are certain frequencies where it won't transmit anything. Like none of that force is getting through. And so you can, sometimes that's good, sometimes it's bad, sometimes you don't want that. Sometimes you want your transmission of force to go through and it doesn't go through. Or sometimes you can take advantage of this by filtering something out. So it's a useful idea. So on Friday, we're going to come back to the vibration example that we did, and we're going to sketch a Bode plot for it. We're going to do a pole zero plot, a little bit of design on it, pole zero plot, and we're going to draw our Bode plots as well.
What time do you think the quiz is going to be up today?
Yeah, so the quiz, I will get the quiz up by 1:30.
It'll close tonight.
Got a little
Sorry?
announcement.
It'll close tonight.
It's canceled.
It'll close tonight, yeah.
The 1 p.m. class. And the second test on Friday will be similar to the